Okay, so the setup that we saw in the previous video is we're trying to solve this. X naught is an approximate solution, and what we want to do is we want to find a delta in a vector space K such that R0 minus a delta is orthogonal to some given orthogonal subspace L, or to some given subspace L. And again, we haven't explained why this is a good procedure to get us to a better approximation or anything like that. Let me just remind you, what is x delta? Well, our updated approximation is going to be x tilde, which is going to be equal to x naught plus delta, like this. Okay, and then R0 is equal to b minus a x0. Okay, and so this is a procedure. This is something that we can do. We want to find a delta in K such that R naught minus a delta is orthogonal to L, and then we're going to define x tilde to be equal to x naught plus delta. So in this video, we're going to start looking at why we might suspect that x tilde defined this way is going to give us a better approximation than what we had before, or why we're going to be pushed to having a better approximation. Okay, but remember that another way that we can state this orthogonality condition would be like if a matrix W, if the columns of a matrix W form a basis for L, we have something like W transpose times R naught minus a delta equal to the zero vector. And well, delta is just a vector in the subspace K, so we can write this as W transpose times R naught minus AVY is equal to the zero vector. Okay, and finally we can write this as, we want to solve this for Y, so we can write this as Y is equal to W transpose A V inverse is equal to W transpose R naught. And for now, we're just assuming that we're dealing with the standard inner product on Rn. Okay, so now, like I said, for this to, like we said before, for this to, sorry, not equals. Got a little mix up there. Okay, now for this to be a well-defined thing, even if we don't take the inverse and just kind of solve this as a system of equations, for this to be well-defined, we need this to be invertible. Okay, and now we're going to give conditions on which that matrix is invertible. So that matrix is invertible. This is proposition 5.1 in the book. I'm not going to prove it. I'm just going to say it. This matrix is invertible, where again W, the columns of W are any basis for L, and the columns of V are any space for K, and A is the matrix that we're trying to solve. Okay, so this matrix is invertible if either of these two conditions hold. A is positive definite, and L is equal to K. So A is positive definite and L is equal to K. Or 2, A is non-singular, A is non-singular, and L is equal to the image of K under A. In other words, we look at every vector in K, multiply it by A, and that gives us a new subspace. Okay, so if either one of these is true, then we know this matrix is going to be invertible, and this iterative method that we're sort of defining is going to be one that at least we have a solution on each step. Whether or not it converges still remains to be seen. Okay, so let me sort of erase this and go over like two different types of projection methods that we can look at. Okay, the first one we look at is going to correspond to this one, and the second one that we look at is going to correspond to 1. So 1, the setup is going to be, in a general sense, the setup will be the same for both of them. Let me just flip to my notes so that I make sure I'm going to get all of the deltas and tildes and everything else right. So find a delta in some subspace K such that R naught minus A delta is orthogonal to L, but in this case, K is equal to L. So we're going to say it's orthogonal to K. So we want to find a delta in K such that R naught minus A delta is orthogonal to K. And actually, let me just, I'm going to rewrite this because I want to sort of say something a little bit more, say something that's going to be true for both methods. So R naught is equal to B minus AX naught. We're going to say that X star is equal to the solution. So that is AX star is equal to B. And we're going to say that the update, our new approximation, X tilde, is going to be equal to X naught plus delta, where, okay, one of two things are going to happen. One, if we're sort of looking at case 1 here, delta is in the subspace K, and R naught minus A delta is orthogonal to K. That's item 1. This is one procedure that we can do. Okay. And if A is a positive definite matrix, this proposition here says it is well defined because that matrix is invertible. 2, the other thing that we're going to look at is delta is in K, and we want R naught minus A delta to be orthogonal to the image of K under A. And that's going to correspond to the second matrix thing. Okay. Okay, so now we're going to have a proposition that, okay, so now we're going to have a proposition that shows why item 1 here is going to give us a good approximation. Okay, so this is, I think, proposition 5.2 in the book. So assume A is positive definite, symmetric positive definite, and K is equal to L. So this is the first case of the proposition that we just looked at. So we know that the matrices involved that need to be invertible are invertible by that proposition. So assume that A is symmetric positive definite and K is equal to L. Okay, so what we want to do, we want to minimize. So we want to minimize X star minus X. Where X is going to be equal to X naught plus delta. Okay. And the minimization is going to happen in the A norm induced by the A inner product, which I'll describe what this is in just a minute. Then the minimizer of let me write it like this. Minimize for delta in K x star minus x naught plus delta. So we want to find the delta that makes this the smallest. Then the minimizer of this is the A inner product is the delta is the delta given by number 1 to the left. That is by this algorithm right here. R naught minus A delta is orthogonal to K. Okay, so let me just remind you what this means here, what the A norm is. So we have the inner product, the A inner product, AVW. So this is the standard inner product. And we can write this as VW with an A there, sort of letting us know that it's defined in this way. And then the A norm is equal to the square root of the A inner product, like this. Okay, so these are just the standard linear algebra definitions, nothing new here. Okay, so now I want to prove why this is true. Okay, so proof. Okay, so why is this true? So delta minimizes x star minus x naught plus delta in the A norm. I'm going to say something that's going to be really ridiculously obvious here. It's almost not worth saying, but it just rearranges this just how I want to. If and only if and only if it minimizes x star minus x naught minus delta. Okay, all I've done there is just change where I have the parentheses. This is a purely cosmetic change at this point. Okay, so delta minimizes the this thing if and only if it minimizes that thing. Okay. Now, the reason that I want to write it this way is because now I want to look at the orthogonal projection stuff that we looked at earlier. So remember, delta is in the subspace K. So this is minimized if and only if the residual is orthogonal in the A inner product to K. So this happens. This is if and only if A times x star minus x naught minus delta is orthogonal to W. So this is the A inner product right here. If and only if this is equal to 0 for all W in the space K. Okay, well, notice how we can rewrite things here. So what's happening? If I distribute this A, so this is let me say this is if and only if, just because I'm going to do a computation here. If I distribute the A times x star is equal to B, then I'm going to have minus A times x naught plus delta. Okay, but now notice this is like this right here is the A inner product of this with W, but now we can view it as just the standard inner product of W with this vector right here. But what is how can we rewrite this? I actually probably didn't need. I actually rewrote it the wrong way here. This is true. It's just not how I needed to organize the sum to make it look like the process. So AX star is equal to B. So this is going to be AX star, which is B, minus X naught, and then, minus AX naught. And then minus A delta. But what is B minus AX naught? B minus AX naught is just R naught. So this is R naught. So this whole chain of implications here says delta minimizes this if and only if R naught minus A delta is orthogonal to W for every W and K. But this right here, this expression right here, simply says R naught minus A delta is orthogonal to K. So through these chains of implications, we see that delta minimizes this if and only if delta satisfies this thing that we have right here, which is the exact definition for the first item here. Okay, so then what that shows us then is if things are defined this way, if you have a subspace K, delta defined in this way is going to give us the best approximation to the solution X star in the A norm. Okay, so notice what we're doing here. We're measuring the distance between X and the solution. We're not directly measuring the residual here. We're measuring the distance between X and the solution. Okay, so that goes for item 1 here. That shows why item 1 is a good thing. Let's see about item 2. Okay, so now I think what I'm about to state is proposition 5.3 in the book. So let A be an invertible matrix. Okay, so let A be invertible, and let L equal to AK. And let L is equal to AK. Okay, then the delta that solves the minimum of delta in K, and now we are going to look at something closer to the residual, B minus AX naught plus delta in the standard 2 norm. The standard norm is given, then, whoops, let me say this as an if and only if statement. Then delta solves this. In other words, delta is the minimizer of this if and only if and only if delta is given by item 2 to the left over here. So R naught minus A delta is going to be orthogonal to AK. Okay, so why is this true? All right, proof. Okay, let's look at the proof of this. So we want to minimize this right here. So what are some ways that we can look at that? So I want to look at it in the following way. I want to look at, so the oops. Oh, no. I broke my chalk. Okay. Well, that's sad. I really like this chalk. Okay. So this, if I want to look at the minimum of this, I can write it as B minus AX naught minus A delta. Now, why do I want to write it like this? I want to write it like this because I want to put it in a format that I understand things. Okay, because delta's in my subspace here. So my goal, let me just remind you that I'm trying to solve A delta is equal to B minus AX naught. Like if I could do that, then I would win, right? I would know what delta is. I would be able to figure out what the solution is. All I'm doing, this is just rewriting that. If this norm is equal to 0, then it means that B is equal to AX naught plus A delta, and that's just equivalent to this. Okay, but the idea is that we typically can't do that, so we want to find a delta that minimizes the error in this sense here, and the error we're saying is in the 2. And delta is lying in the space K. So the way that I want to write this, the way that I want to think about this is as the minimum. I want to get it to look as much like a matrix vector minimization problem that we looked at before, just because it helps me think through things. So we're going to have B minus AX naught minus A. Okay, so what is delta? Well, delta is any vector in K. Let's say we have a matrix V whose columns are a basis for K. And I can write this as V times Y. Okay, well, how do I find the Y that minimizes this? Okay, well, remember, if we go back to what we saw before, the vector that minimizes B minus mx is going to be the vector where B minus mx is orthogonal to the column space of n, where we're doing all of this in the standard norm. Right? That's what we saw in a couple of videos. The x that minimizes this is going to be the x where the residual B minus mx is orthogonal to the column space of n. Okay. So what does that mean? This whole big thing is the residual. Yes, okay. This whole big thing is a residual, and so what we're saying is we want this to be orthogonal. Excuse me. We're saying we want this to be orthogonal to the column space of AV. So what we're saying is we want B minus AX naught minus AVY. We want this to be orthogonal to the column space of A times V. In other words, we want this to be equal to 0 for all Z. Okay, because as Z runs through its space, AV times Z is going to run through the column space of AV. Okay, but notice we can write this a little bit differently now. V times z, as z runs through its space, v times z is going to run through the subspace v. So I can write this in this form. I'm going to have a times u, and we want this to be equal to 0 for all u in v. We want that to be equal to 0 for all u in v. Okay, but what about a times u? U is in v. So as u runs through v, a times u is going to run through L because L is equal to a times k. So how do you form this subspace L? Just every vector in v, you multiply by a, you get a times u, and that's going to give you L. So this is true for all vectors u in v. So as u runs through v, au runs through L. So we can write it in this form right here. W, and this is going to be for all w in L, which is equal to a times k. Okay, so now let's come back over here to see what we can get. How can we rewrite this a little bit differently? Okay, so b minus ax naught, that's just equal to r naught. So we're going to have r naught minus avy w is equal to 0 for all w in L. Okay, but remember what v times y is. V times y is just equal to delta. So v times y, we can just write this as delta. It wasn't really even necessary to make that switch, but for me, kind of psychologically, in a way, it was necessary for me to make that switch. Anyways. Okay, so there we have it. No, it actually probably was necessary to make us so that we could work through this right here. Anyways, whether or not it was strictly necessary, it helps me psychologically to work through the logic here. Okay, so again, just to overview, we want to find the delta in k such that this error is minimized. That is, we want to minimize this error. We're just using the fact that delta is in the subspace v, so it's equal to v times y for some vector y. And so now we want to minimize this. But now we can think about this as solving the matrix vector, or as solving the equation avy is equal to b minus ax naught. Okay, and we saw before that the solution to this, the minimization solution to this, is going to be the one such that this vector right here is orthogonal to the column space of that matrix, A times V. But the column space of that matrix, A times V, well, L is equal to A times K, and V is just, its columns are a basis for K. So when we say that the residual vector is orthogonal to the column space of A times V, we mean that the residual vector is orthogonal to A times K, which is equal to L. So in other words, we want this vector right here to be orthogonal to L. In other words, the inner product of this vector and W is equal to 0 for all W and L. And now we simply rewrite B minus AX naught as R naught. And we have R naught minus A delta is orthogonal to L, which is exactly what we have for this option here, for this format here. Okay, so that is it. This gives two basic selections of L given K, and it shows that there is some sort of optimality, that defining a projection method this way gives us optional approximates for some version of approximate.